Internet. This is Marcus Auer from MinaReversion.com, and today I'm going to introduce you to a little tool I wrote called Pseudo-Geometric Brownian motion that is used to model complex financial products with path dependency in R. And before we start our analysis here, I want to refer you to my homepage where you can find all the information of this video and even more, nicely summarized in a little article I wrote. And at the bottom of this article you can also find a download link for the R script that we are going to be using. In case you don't want to type along with me in R yourself, you just download that file and be done with it. Now, before we jump right into modeling, I want to talk about Brownian motion for a bit. So, as most of you probably know, since you've clicked the title of this video, Brownian motion was developed to model the motions of particles in gases, and these motions had nice properties. They were usually normally distributed. Now, as everyone who had ever in his life had contact with quantitative financial data knows that in finance, normal distribution is not really the best thing to do. So if we look at a path of a security, it would look something like this. And if we assume this path here was simulated using geometric Brownian motion with an implied normal distribution for the innovations, what does that mean? Well, let's look at the normal distribution first. So if we have a normal distribution, it should look something resembling this. Well, please don't pay attention to my awful drawing here, but you get the idea. Now, in finance, we know that returns, which are the innovations for this series here, are not really normally distributed. They're usually somewhat leptocratic, which means they have heavier tails and more weight in the center of the distribution, and they usually have a little negative skew, which means that their mode is somewhere above zero. So if we would draw this distribution, of course please don't take my drawing here as a model drawing for any distribution, you would see that we have a lot more weight down here in the tails and up here in the center. What does that mean? Well, if we took this exact distribution here and modeled the same path, maybe we would get something that looks more like this. As you can see, there are maybe a few more smaller returns, but some large and very infrequent positive and negative returns. And of course, this has implications for securities where there is some kind of path dependency inherent in them. So if we assume there is an arbitrary derivative, let's call it an option, that has some kind of knockout price. Usually with knockout certificates there is a price, and if the security falls below that price, the knockout certificate gets cancelled. So with the normal geometric Brownian motion, we see some kind of smooth transition here that can be somewhat anticipated, because when you're up here you're highly unlikely to see a dip that takes you right down to the knockout price. But with this distribution here, this blue one, we can see that when you're up here you have no idea of knowing if there's some kind of extreme negative event around the corner that takes you right down below the knockout price, and your security is basically worthless. So with that in mind, let's fire up R. So as you can see, I have a custom load up screen. You don't need to be concerned by it. It's gonna look different for you, I know. And as you already see, I'm going to execute my script here in RStudio, not because they paid me to do that, but I think RStudio is just the most accessible application or user interface for working with R. But if you want to run this code here in standard R, there's nothing stopping you. It's just that I like to work in RStudio because when I'm plotting things, I can easily toggle around down here, and it's also a lot more user friendly. And if you want to show people stuff like I'm doing right now, it's much more easier to follow. And yeah, so let's get right into it. As you can see, we need to install a package first, the QuantMod package. The QuantMod package is not really needed for our code to run. It's more a utility function that we need to download stock prices from Yahoo Finance, and also one of the dependencies of QuantMod is of course XTS, and we need XTS to get all those nice advanced time series objects for R. So let's get right into it. I'm going to skip the first step, installing QuantMod, because I already installed it a long time ago. And next we will require QuantMod. Requiring loads attack package, and as you can see down here, when we also installed and loaded XTS and SU, which are the time series packages that are mostly used in finance in R, and there's some information that does not concern us. So let's get started by downloading price data for AT&T for the time period between 1985 and December 2015. This is actually the most data Yahoo Finance has to offer. So after a little wait, you'll see AT&T pop up here in your environment, and it's an XTS object from 1985, just as we wanted. However, we're not interested really in prices because we want to model returns, and there is a nice function called period return in QuantMod that lets us calculate monthly returns with one function, and this is what we're going to do next. And we also assign it into a normal time series object with just frequency 12. Now that we have our returns calculated, they are also in the environment up here, we should get an idea what we're dealing with. So it doesn't really matter if you're working with data that's actually in need of visualization or not, because I'm one of those people who think that if you're working with data, you should always look at it first, and that's what we're going to do. So we see here a nice little density estimate for our AT&T returns with the standard density function. We didn't mess around with the bandwidth. You know that bandwidth has big impact on how this curve down here looks like. But what we're doing next is actually creating an overlay and adding a normal distribution to this plot to see how our returns for AT&T actually fare against a normal distribution with the same mean and standard deviation. And whoops, we already see what we kind of prophesized first. Let's make this a little bit larger. We can see here that, as we expect, there are heavy tails, very heavy tails, especially on the negative side. And there's a higher density of returns here around the center, but above zero. So this is kind of the negative skewed heavy tail distribution we are very accustomed to see in returns. So AT&T is not really an outlier here, but it's more the rule of what you see when working with returns in financial data. Oh, I also forgot you could put a rug there, but it's not really telling us anything beside what we already know. Next, we're going to do a Kolmogorov-Smirnov test, which is a test to see if two distributions are the same. And we need to set a seed here first, so you can replicate the results of this function, and this just ensures that when I'm hit enter next, you will see the exact same thing on your screen. And if we do the test here, we see that our p-value, which is kind of the telltale value of this function, tells us that we have a 2% chance that we get a difference in distributions like we have here between the normal distribution and the actual empirical distribution. What this tells us in simple words is that those distributions are very different. Now, how does this all connect to geometric Brownian motion? And here comes probably the thing you anticipated most. We are going to create functions to model such returns. And our first function is the standard GBM function. I wrote this function myself, but there are GBM functions in the SDE package, I think, but I wanted to write it myself so you can see what's going on. So there's nothing special about this function. You see down here, this is the main part. This is basically where the geometric Brownian motion is. You can see here that we have two parts to this function. The first is x is the starting value, so the last price in the series. Mu is the mean of the returns. dt in our case will be 1. And down here is where our future problem is. This is the innovation part. We can see here that the innovation is calculated as a random number with a mean 0 and a standard deviation 1 times the square root of the time difference, which is 1 in our case, and the standard deviation of the returns times the last price. And our main problem is actually only here because of this random number generation that only draws a random number from a distribution with mean 0 and standard deviation 1. And this is what we are going to alleviate. So let's log in that function first. I'm going to execute all that code, and we should have our function down here. Perfect. So what can we do to alleviate our problem? And I opted for pseudo-geometric Brownian motion that uses kernel density estimates. Now, kernel density estimate is what we have seen in this graph here, the black line. This is a kernel density estimate. It's not actually the real data, but it's a smoothed distribution of the data we have. And it would be better if we would draw from a distribution that looks exactly like our kernel density estimate rather than the normal distribution. And that's actually what we're going to do. So there's nothing different in the general setup except that we only need to, for this function to work, we only need the starting value, the returns as a vector, and the number of steps ahead we want to forecast. And we see here that the main function is actually very, very simple because we only take the kernel density of our returns, or to be precise, of our demeaned returns. Then we're just going to sample from this kernel density and put it back in. That's all. That's all the magic. We're going to start with our starting value, then add the mean and the sample value from the kernel density estimate times the starting value, which is obviously the return, the absolute return, and add it all together, and that's it. That's all we're going to do. So how does this compare to our standard geometric Brownian motion? We will see. Again, log in the function, check if it's here, yes, and we need to define our starting value x, and we're just going to assume it's the last value in our price series, not return series. That's important to remember. So our x value is $33 and something, and again we're going to set our seed just for replicability. And next we're going to use my GBM function to estimate a price path with the exact same length as our empirical data. And we're going to do the same for our pseudo-geometric Brownian motion. Again, we need to set seed for replicability. Now, we have two vectors with prices in them forecasted from our GBM function and pseudo-GBM function, respectively. What we are actually interested, however, are returns, and therefore we're going to, again, calculate returns. However, this is not a time series object, so we need to use the standard log diff -1 to calculate returns. If you don't know what it does, it's actually just calculating the log of the series, then first difference it, that way you get log returns, and the -1 cancels out the NA value that's in the first cell. Now that we have our returns, maybe we want to visualize how we did. So again, we are going to calculate the densities for our empirical returns ATTR and the densities for our GBM and PGBM respectively. And if we plot those all together, I've opted here for an option where I create the plot first and add the lines in back later. We will see the red line here is the standard geometric Brownian motion, which falls very, very short of what we expect it to actually accomplish, because the black line is the distribution of empirical returns, and we see, as we would expect, a more smooth distribution that's inherent by the normal distribution, and very, very slim tails here. In comparison, the blue line, our pseudo-geometric Brownian motion, is much, much more closely resemblant of our empirical returns. Of course, there's some problem here, but if you would increase the forecast range, if you would increase the number of values you have for the pseudo-geometric Brownian motion, the density would actually approach this empirical distribution and match it perfectly with a large enough sample size, while the red standard geometric Brownian motion will always be different from the empirical returns, whatever you do. So again, if you're not the kind of visual guy that I am, and you want some formal proof that these distributions actually are different or more resemblant of the empirical distribution, we're going to use the Kolmogorov-Smirnov test again. And first we're going to compare our empirical returns to our pseudo-geometric Brownian motion returns. And we see that we have here a p-value of 0.4, which is, as you remember, our first p-value for the normal distribution was something below 5%. We're here now with 40%, so we see that those two distributions cannot be with statistical certainty be declared different. In turn, however, if we compare our empirical returns to our standard geometric Brownian motion returns, we see a p-value of 0.02, which means that those two distributions are most certainly different from each other. This goes to teach us that our pseudo-geometric Brownian motion is much, much more precise in replicating our past returns. Now that we have this very simple example behind us, we can tackle a little bit more complex example. And for this, I want you to imagine a security that's called Rente Chance Plus. It's a product offered by Generali Germany. This Rente Chance Plus product offers investors the opportunity to participate in the Euro Stoxx 50 index without any downside. And how it works exactly is that you get a 20% participation in the upward returns of Euro Stoxx 50 index. So if you have a 10% return in 1 year on the Euro Stoxx 50 index, you would get 2%. And you get no downside. So if the Euro Stoxx falls, your invested capital stays the same. And that also applies for your accumulated returns. So if you have a year where you have a return of 10% and you get your 2% participation, and the next year has a negative return, you will still have your invested capital plus your 2% return from the prior year. However, there is a cap on a 15% returns. So if Eurostoxx 50 would at any given year exceed 15% return, you would get none of it. So you would always be capped at 15% times 0.2. Of course, generally can alter these values, but for the sake of the argument, we are going to assume that over the 20-year investment horizon, this participation rate and the cap rate will stay constant, and we are going to evaluate how the price of this security will change with an implied normal distribution with our pseudo-geometric Brownian motion in contrast. So again, as we did before, we are going to download the price data for the Eurostoxx 50 index. Unfortunately, Yahoo Finance only provides data back until 1990, but that's fine for our purposes. Again, this is an XDS object and we want monthly returns. Here are our returns. Again, we're going to look at it and compare it to the normal distribution, and as before, kind of the same picture as before, we see here that the distribution of returns is even more skewed than the AT&T returns, and again we have heavy tails, this time on both sides actually. And if we perform our trusty KS test, we see that, well, our p-value of 0.06 is actually suggesting that our distribution is not quite normally distributed. Again, as above, we start with our starting value x, the last price of the Eurostoxx in our data, which is 3,286. And then we're going to do something different. Now, before you execute the next few lines, beware, we are going to replicate this code 10,000 times. So we're going to estimate 10,000 paths for each method, ranging 20 years in the future. So we have a path with length 240 replicated 10,000 times. And this, of course, will take a while depending on your computer speed. Just bear with it. It shouldn't take that long. And do the same thing for the pseudo-geometric Brownian motion. And we're done. Now, another feature of that security is that it's evaluated only once a year. So usually at the end of the year or day you actually entered into the security contract, you're going to evaluate has the Eurostoxx increased or declined, and if it has increased, by how much. And therefore we're going to actually, now that we have a series of prices that's actually monthly prices for the next 20 years, we're going to limit that to only the last price value in a year. And that's what this line does here. It just converts our simulated prices into a time series object that only contains the last price in the year. And again, we're going to want to look at our returns just as before. And now that we have our returns, we can actually remember our thus far S1.R and S2.R are the returns for the Eurostoxx, and that's not what we are interested in. We are interested in our constraints and our security that those constraints apply to. So what we're going to do is we're going to apply our constraints to the returns, and we start off by actually setting 0 every return in the series that's below 0, because as you remember, we don't get negative returns on our security. And next we want to evaluate our security in terms of our participation and cap rate, because as you remember, if you have a return larger than 15% on the Eurostoxx, you don't get anything from it. So these two lines actually compute your return that you're actually gonna get from that security. So if it's larger than 15%, you only get the 15% times the participation rate of 20%, otherwise you get the return times participation rate. And what we're actually going to be looking at is not the returns year over year, but rather the returns over the entire period. So we're going to calculate returns over 20-year horizon. And the nice thing, since we're using log returns, is that we just can sum them up, and that gives us the return for the 20-year horizon. And this is our S1 and S2. And now comes the moment we all have been waiting for. How do those two values differ? And remember, what we are seeing here now is not actually the returns every year, but the return in the final year. So how much did we earn over the 20-year horizon? We remember we're going to see only positive values because we have constraints that restrict us from going negative. And what I'm going to do next is actually copying this graphic here into Paint, so I can draw around on it. And what we're seeing here is that those distributions, remember that red is the standard geometric Brownian motion and blue is the pseudo-geometric Brownian motion. Well, they don't look that different, but remember, we're only positive here. We're starting from 0. And remember, when we looked at our distribution of returns, we had a large, heavy tail in the negative section. But this does not concern us for this security because we don't get to have negative returns. So it's not surprising that we see a similar tail here in the negative side. And also on the positive side, since we've seen there's only a slight deviance from normal distribution when it comes to the Eurostoxx returns. But we see that, blue is a little bit more expressed than red here. So there is a heavier tail on the right. And maybe what's more important, because those differences are not really substantial, but we can see here that the standard geometric Brownian motion is somewhat centered around here, whereas the pseudo-geometric Brownian motion clearly, very, very clearly exhibits this negative skew that we have seen in the distribution of Eurostoxx returns. Because you see, the mode probably, I've intentionally used a very small bandwidth here so you can see these small differences. The mode is a little bit more to the right here probably, and then we have a very steep decline. How much are those two distributions different from each other? We want to know that. So for our trusty Kolmogorov-Smirnov test, we get a p-value that's extremely small. So this would suggest that those two simulated distributions are substantially different from one another. However, please keep in mind that we are seeing an estimate here for the 20-year return based on 10,000 replications. So the Kolmogorov-Smirnov test has this unfortunate feature where it produces a very small p-value whenever you use samples with a very large size. So maybe take this value here with a grain of salt. However, remember we set out on this quest for knowledge here to find out how our evaluation of this rente chance plus security would differ if we used our pseudo-geometric Brownian motion rather than our standard geometric Brownian motion. And to do so, we're going to compare the two means of the distribution, because that's what you're actually interested in the end. And what this tells us here is that the mean of standard geometric Brownian motion distribution here, the red one, is actually smaller by 0.6% compared to the distribution achieved with pseudo-geometric Brownian motion. So what does that mean? Well, if you are generally the counterparty in our case here who offers this security, and you're going to model the security because you want to know what the return will be so you can buy, I don't know, a bond that pays this kind of return that you're going to estimate, so you have some kind of reinsurance for your product. And when you calculate this and you get the mean S1 here, you're going to actually underestimate the return by 0.6%, that you're going to need to reinsure for your security to be profitable for you. Now, 0.6% doesn't sound like much, but if you consider, let's say these products are usually very popular, so assume that Generali issued a volume of 1 billion for these securities. If you underestimate the need to reinsure those securities by 0.6%, you're actually going to fall short for 6 million of return, and that's substantial. Of course, before you call Generali and tell them of their mistakes here, probably they have some smart people there looking into this, and of course don't forget they can actually control the participation and cap rates for the security, so they have many ways of not running into this situation. But still, if they're using the normal distribution, they're always going to be underestimating their return they need to reinsure by quite a substantial amount actually. However, our nice little method here has some drawbacks as well, because it could be the case that our returns here are somewhat serially correlated, as we would see especially in less developed markets. Of course, there's the Euro stocks, so it's a highly developed market, but if we're going to China or India, probably, there is the possibility of some autocorrelation in returns. And if we have autocorrelation, our nice little pathing here is not really going to cut it. However, if we look at the ACF, we see the first autocorrelation is insignificant, so we can rest assured. However, there are some other problems with our approach here. If we go back to the density estimate for Euro Stoxx returns, we assumed by using the pseudo-geometric Brownian motion that this black line here is actually the real world. That's actually what's going on, and this distribution will persist in the future. And the reason why a lot of people are still using the normal distribution is because they assume, hey, yeah, that's the black line, that's what we've seen in the past, but that's not really representative of the underlying structure of our returns. Maybe if we go 10,000 years in the future, we're actually going to see a distribution that's quite normal. Maybe what we see here, the black line, is only temporal. Maybe that's just an expression of the past few decades, and they could be right about that. And then again, remember that our pseudo-geometric Brownian motion does not care about the bandwidth. However, if you increase the bandwidth enough, it will actually become probably something that's so close to the normal distribution that the difference doesn't matter. If we go back to our pseudo-geometric Brownian motion function here, you see I left some arguments open for the user to enter, and those arguments are going to be passed into the density function. So if you want to specify the bandwidths for the density estimate yourself, you can do that. Up till now, we only trusted into the built-in bandwidth selector for the density function, but this could very well be wrong, and this could very well be what's actually going to cause our 0.6 difference here. So be very careful when you're using this approach I just introduced you to. It's nice to play around with it, but beware, as all the approaches used in finance, it has its drawbacks, and also it's not really founded in theory. It's just a parsimonious thing. It works well for what you would expect it to do, but there are no fancy papers written about it. There are no nice formal ways to express it if you need to, and it's more a stress test thing, I would say. It's not really something I would advise you to use every day when working with geometric Brownian motion. However, I hope that you like my tutorial here. If you did so, leave a like on the video, comment on it, and tell me what you liked, tell me what you didn't like, what you wanted to see probably added to it, and yeah, thanks for watching.